Okay, so kind of it's a tedious computation, but the basic principles we had already discussed. I do strongly suggest you to do it on your own. Now, any questions up to here? In the second hour, I would rather go over some examples. Almost throughout this course, most of the time when we say about examples, we will look at the ideal gas. So do you have any questions up to here? Now, all of our discussions about the microcanonical up to here was basically if you apply it to a classical system. Remember, we were discussing about the density of the copies in the phase space, and this density is basically proportional to e to power minus beta e. And so if you want to calculate the average of any quantity, remember, it's just a dp dq rho of pq times f as a function of pq divided by this is the average. And for the partition function, we will identify the partition function, let's say, for n particles as, let me write the dimension also, d3n, d3nq divided by 2 pi h bar raised to the power n. So this factor 2 pi h bar to the power 3n, sorry, we had already discussed. It's basically, well, quantum mechanics tells us that you cannot isolate any state to one point in the phase space. The best you can do is you can just localize it to not a point but a volume of 2 pi h bar to the 3n. So we had seen this factor from the free particle, also from the harmonic oscillator. Both of them will give me the same number. And furthermore, when we are calculating the averages, that factor we basically don't care. In the ratio, that factor will just cancel. And there's also the Gibbs factor 1 over n factorial. So this is the partition function we will use to study a classical system. Now, of course, if these okay, so you can say that these P's and Q's, if you imagine gas systems made up of molecules, you can just separate the center of mass, momentum, and coordinate, and internal coordinate and momentum. In that case, you can say that P and Q are the center of mass coordinates, and then in addition to these integrals, you will have additional integrals over the relative momentum and relative coordinate. And typically, let's say for the ideal gas, let's say the energy will be just p squared over 2m plus, well, let's say just p squared over 2m, pi squared over 2m, or rather, let me even write it as, okay, this is the energy of n particle, sum over all the particles ai of pi and qi. The energy of the n particle system, let's say that I can write it as the sum of energies of each individual particles. Well, this I can do if there is no interaction between the particles. I'm just ignoring the potential energy between the particles making my system. But if, let's say, there are external potentials, well, I can also treat it in the same way. External potential doesn't change this treatment, but interactions between the particles will change this treatment. Now, if I do this, let's say this Qn becomes 1 over n factorial let me write this as d cube pi d cube qi divided by 2 pi h bar cubed times product over I again of e to power minus beta ei. And which will also be 1 over n factorial qi. But you see that integral over there is nothing but what I would write for the partition function if I have a single particle only. So let me just call this Q1. So the partition function for an n-particle system, if the particles are not interacting with each other, can always be written as the partition function for one of those identical particles raised to the power n divided by n factorial.
Can I ask something? Where does the 1 over n factorial come from? Indistinguishability, right?
We just added.
Yes, but my question is, if this is a classical system, we just still have 1 over n factorial.
Yes.
But a few lectures ago, I thought we discussed that in classical systems, you can trace particles, thus there is no indistinguishability. So every particle is distinguishable.
Exactly. And that kind of, I mean, you see, it was already known before quantum mechanics that we had to introduce this n factorial. Because otherwise, if you just put two identical gases, remove the separator, the entropy shouldn't change. If you don't have that n factorial, the entropy does change, even if you have identical gases, and there is no entropy of mixing in that case. Now, the origin of that n factorial was not known, but that solved the problem of mixing of identical gases. Now, quantum mechanics tells us where that comes from. Now, classically, as you said, we don't need to introduce that. But we know that we have to introduce it from experiments, from thought experiments at least. And there's no reason for introducing that in classical physics. But if we don't introduce them, the results we obtain are not correct. We definitely know that. And then quantum mechanics told us where it came from. And it also told us that that is an approximate solution to the Gibbs paradox, not the exact solution. So is this kind of also any other questions? Okay, this also kind of tells us that if you want to study this non-interacting particles, it's enough to study just one of them. Q1 is enough. Furthermore, if there are no external potentials, Q1, which will be a function of V and T, will be just V. You see, this d cube Q integral in the definition of Q1, exponent doesn't depend, if there are no external potential, energy doesn't depend on Q. If energy only depends on the momentum and not the position of the particle, that will be the case if there are no external potential, then Q1 is proportional to V. The n-particle partition function is V to the n divided by n factorial, whatever this function f of t is. And what else can we say? Then remember, we define the free energy F times beta to be minus the derivative with respect to, no, minus the logarithm of Qn, sorry, which is minus n logarithm of V minus logarithm of whatever this function is, and plus n logarithm of n minus n. I just also use the Stirling approximation. So free energy is minus nkt logarithm of v minus logarithm of f of t times kt plus nkt logarithm of n minus nkt. So this is the free energy of the system in terms of this unknown function f of t. We will calculate that for several cases. Well, if we know the free energy, we can determine the pressure. The pressure is nothing but the derivative of the free energy with respect to volume with a minus sign at fixed t and n. Well, the only volume-dependent term is the first one. If I take the derivative, this will be nkt over v, which tells me that PV is equal to nkt. So you see now, in this canonical ensemble, the derivation of the equation of state was, well, basically half a page. Entropy is the derivative of the free energy with respect to temperature at constant volume and number. Well, without knowing f of t, we cannot do much over there. So we have to calculate the f of t to calculate other thermodynamic quantities. So let's look at the, you see, f of t, we had defined it over here. And q1 is this function. And we are looking at the case where the energy depends only on momentum. So this is v over 2 pi h bar cubed, d cubed pi e to power minus beta ei of pi. Now, almost all the variations from here, let me also write d over here. There are lots of variations in these kind of problems. You can be asked for what happens if we are not looking at a 3D dimensional gas, but you look at a gas that is trapped between two parallel plates. And so the gas particles can only move in 2 dimensions. Or you can be asked what happens if you are looking at a gas which is trapped in a tunnel. So they can only move back and forth, and they cannot move in other dimensions. In that case, t will be 1, 2, or 3. Or you can be asked what happens when you are looking at a non-relativistic gas, in which case E of pi will be p squared over 2m. Or you can be asked what happens if you are looking at a highly relativistic gas. It's p times c. So the only thing that will change is just put in the corresponding expressions over there. So as a concrete example, let's look at the non-relativistic case in 3D. In that case, Q1 is V over 2 pi h bar cubed, d cubed p e to power minus beta p squared over 2m. Well, I can go to the spherical coordinates to evaluate this integral. This is V over 2 pi h bar cubed. The angular integration will just give me 4 pi. From 0 to infinity, dp p squared e to power minus beta p squared over 2m. I have to evaluate this integral as a function of p. Of course, you can go ahead and do integration by parts, etc., but let me use a different trick. This is V over 2 pi squared h bar cubed. I just canceled the 4 pi's. D over d alpha with a minus sign from 0 to infinity, dp e to power minus alpha p squared. If I take the derivative with respect to alpha, it just brings down a factor of p squared. Once I take the derivative, I will set alpha is equal to beta over 2m. Well, that integral is a Gaussian integral whose value is square root of pi over alpha. I take the derivative and set alpha is equal to beta over 2m. Now I can take the derivative. The derivative of that expression will be, there's a square root of pi, 1 over 2 alpha to the power minus 3 over 2. Evaluate that alpha is equal to beta over 2m or 1 over 2m kt, k being the Boltzmann constant. So this is v over 2 pi to the 3/2 power h bar cubed. There's a 4. This is 2m kt to the power 3/2. So this is my Q1. So whatever is multiplying v is what I called f of t. Questions up to here? So Qn by the way, here there's another factor of 1 over 2. Gaussian integral from minus infinity to infinity would have been pi over alpha. Since this is from 0 to infinity, it's just half the value. The derivative brings up an additional 1 over 2, so here I have 1 over 8. So that is, yes, this should be the answer. 1 over 8 is 4 to the power 3/2. So I put the 4 here and do the cancellations. Qn is v to the n divided by n factorial mkt divided by 2 pi h bar squared to the power 3/2. F is minus kt logarithm of Qn, which is minus nkt. Yeah, sorry, there's a 3n over here also. Minus kt n logarithm of v plus nkt logarithm of n minus nkt. This is just a minus logarithm of n factorial times minus kt. Minus 3n over 2 kt logarithm of mkt over 2 pi h bar squared. This is the free energy, which, let me also slightly simplify it, nkt logarithm of v over n minus nkt plus, no, minus 3 over 2 nkt logarithm of mkt over 2 pi h bar squared. Okay, is this an extensive function or an intensive function? The free energy, like the total energy, has to be an extensive function. Is this an extensive function?
Not for
Well, you see, what do you mean by extensive function? Let's say you take your system, just double your system. If it's an extensive function, it should be doubled. So if you double your system, n is doubled, v is doubled, so v over n is not doubled. So this logarithm doesn't change, but there is this overall n. So the first term is an extensive function. All the other terms are extensive. N is doubled, t doesn't change if you double your system. So this is an extensive function. This is an extensive function thanks to this factor over here, dividing the v. That factor is this term. Thanks to that term over here, f is an extensive function. But that term comes from dividing by n factorial. So just knowing that the free energy has to be extensive, you know that you have to divide by n factorial. Why? Well, classical physics doesn't tell us that. Doesn't tell us where that n comes from. Because in classical physics, there is no concept of indistinguishable particles. All particles are distinguishable. Quantum mechanics tells us where that n factorial comes from, but that came later on. Well, what is the energy? I remember the free energy is U minus Ts. So energy is F plus Ts, but S is derivative of free energy with respect to temperature, which we can also write as just take the T squared out. This is derivative with respect to temperature of F over T, multiplied by T squared. Well, if I divide by T, the only T-dependent term is this logarithm, because all the other terms have the T as a product and nowhere else. If I divide by T, those terms become independent of T. So the free energy of the system becomes minus T squared times minus 3 over 2 mkt times derivative of logarithm of T is 1 over T. Now there's no T, because I divide by T. So this overall factor T doesn't appear, it's cancelled, so 1 over T, this is 3 over 2 nkt. Now if you compare this to what we had done in the microcanonical ensemble, you remember there we had this all 3n dimensional space, we had to calculate the 3n dimensional volumes, etc. And only after that we could obtain the internal energy, the pressure, and the equation of state, etc. But here in the canonical ensemble, the great advantage over here is this identification. At least for non-interacting systems, you can write the partition function of the whole system in terms of the partition function of only one of the particles making the system. And well, here, kind of in some steps, I wrote down too much details, but on your own, you can just derive all these properties in just one page. Any questions here? So let's look at another problem. This time from the perspective of quantum mechanical systems. This will still be valid. I will just imagine I have n harmonic oscillators. Q1, remember, it's the partition function of one harmonic oscillator. That is nothing but sum over e to power minus beta E n, and ranging from 0 to infinity, and the energies of the harmonic oscillator is h power omega n plus 1 over 2. This is equal to e to power minus beta h power omega over 2. This is the 0 point energy. If we just sum over from 0 to infinity of e to power minus beta h bar omega raised to the power n, q1 is equal to e to power minus beta h bar omega over 2 divided by 1 minus e to power minus beta h bar omega. This is my q1. Or if you would like to simplify it even further, write it in different forms, this is 2 over cosine hyperbolic of beta h bar omega. No, sine hyperbolic. Whichever one you prefer. Well, then Qn is for the harmonic oscillators, there is no 1 over n factorial. Why not?
Can you repeat the question?
Now, for the harmonic oscillator, you see here, we said that the free energy of the n particles is q1 to the n divided by n factorial, and n factorial was there to resolve the Gibbs paradox. But in the case of harmonic oscillator, we will not have that n factorial. Why do you think that is? It will again come.
Is that n particle or n excitations of one particle? In that
No,
case?
I am looking at n harmonic oscillators. You see here, I am summing over all the excitations of one oscillator, and then I obtain the partition function of n oscillators from that partition function of one of them. But I don't divide by n factorial. It's again comes to the whether you can distinguish the harmonic oscillators or not. You see, when you are looking at harmonic oscillators, what you do, you have particles oscillating around a fixed point. In principle, you can have many oscillators oscillating around different points. For example, a solid, take a solid. There are many atoms making this one, but every atom is oscillating around its equilibrium point. And so you can distinguish the oscillators from looking at their equilibrium points. So that's why we don't have 1 over n factorial, because they are distinguishable. Now, you see, we said that classical physics tells us that all particles are distinguishable. I can follow their trajectory and distinguish them, which one came from there in principle. Even if I don't do that in principle, I can follow them. Quantum mechanics tells us that no, you cannot follow their trajectory. So if you have two particles over here, and at a later time, if you observe two identical indistinguishable particles over here, it might be that they just moved like this or like this. You cannot distinguish the two because you cannot follow their trajectories, even in principle. Now, in the case of harmonic oscillators, they are oscillating around a fixed point. They will stay there. By just looking at around which point they are oscillating, I can distinguish them, even quantum mechanically. Even if I treat each oscillator as a quantum mechanical object, I can distinguish them. Because that point is fixed. So every oscillator comes with its own equilibrium point, and I can distinguish them.
Hocam, is this also valid for perturbated cases?
Well, it depends. For example, I gave you the example of a solid. So what happens in a solid if you heat them? Now, each oscillator is oscillating around its equilibrium point. If you heat them, they will start oscillating wilder and wilder. They will be displaced from their equilibrium point more and more. Eventually, they will be able to overcome their potential barrier. Now, that is what we call melting. So each one of these oscillators are now free to move throughout your volume. So it became a liquid. Before, each atom was fixed around an equilibrium point. And so once it melts, all the atoms are free to flow around. But now, when it starts flowing around, it's no longer a system of oscillators. So it's a perturbed system, but once you put sufficient perturbations, the system completely changed. But if you just say that, okay, maybe the potential is not harmonic, it's not just quadratic, I have the cube, the fourth term, well, so what? They are oscillating around some point. And since each one will be oscillating around a different point, I can distinguish them.
Point, do you mean points in space?
Yes, point in space.
So we don't have.
One over here, another one oscillating here, another one oscillating here. This is the model we have. Of course, if you give too much energy, they will be oscillating over here. Eventually, they will be just moving almost freely. So when that happens, your solid has melted.
So in this model, do we assume that none of the oscillators touch each other?
Yes.
Okay. So enough free space between them. Enough free space between them.
Yes.
So we can pick out.
The free energy is minus kT. Now let me just continue along that line. Qn is q1 to the power n, which will be h power minus n beta h bar omega over 2 1 minus h power minus beta h bar omega raised to the power minus n. This is my Q1. The free energy will be minus kT logarithm of Qn, which is minus kT n kT logarithm of Q1 minus n kT logarithm of Q1. That's where there's logarithm of Q1 will be minus h bar omega over 2 times beta minus logarithm of 1 minus h power minus beta h bar omega. This is my free energy. So this will be, there's a minus sign also over here. H bar omega over 2 times n. Remember, beta is 1 over kT. So the overall factor kT cancels that beta. Plus n kT logarithm of 1 minus h power minus h bar omega over kT. This is the free energy. I can talk about the entropy. The entropy will be minus the derivative of free energy with respect to temperature. Well, you see, this is nothing but the 0-point energy of n oscillators. So the free energy also has that term. Well, the entropy will be the derivative with respect to temperature. That will be minus nk times logarithm of 1 minus h power minus h bar omega over kT. This is from the derivative of the overall T. And minus nkt, now I'm taking the derivative of the temperature. That will be minus h bar omega over kT squared, h power minus h bar omega over kT, divided by 1 minus that exponent. Yeah, if you like, you can simplify it further. Let's calculate the energy. The energy is minus T squared derivative of free energy over T with respect to temperature, keeping everything else constant. Well, the free energy is over here, so the energy will be minus T squared times, if I divide by T, there is a contribution from the first term, which will be minus h bar omega over 2t squared n. Yeah, this is nothing but the 0 point energy. And then there's also from the derivative of the temperature, which will be e to power h bar omega over kt, h bar omega over kt squared, divided by 1 minus e to power minus h bar omega over kt. So this will be n times h bar omega over 2, that is the first term. That is the expected term from the 0 point energy, plus minus h bar omega over k e to power h bar omega over kt divided by 1 minus. Well, did I forget some minus somewhere? No, there's a minus sign over here. Well, so I'm taking the derivative of this logarithm. There is a minus sign here, another minus sign in the exponent. There will be a third minus sign from the derivative of 1 over t in the exponent. So there is a minus sign over there. So this will be n times h bar omega over 2 minus h bar omega plus 1 over 1 minus e to the power h bar omega over kt. Okay, there is a third factor I am missing. Free energy is, okay. So here there is a k, because free energy over t, there is a k over here and k. So that is this k over here, and in fact there is an nk that I forgot to add. So this cancels this one. I have a factor n. This is the energy of the harmonic oscillator as a function of temperature. And this E, as t goes to infinity, for very large temperatures, there is an nh bar omega over 2 plus nh bar omega 1 over 1 minus 1. You see, if t is infinitely large, h bar omega over kt is very small. So I can make an expansion and keep the first term. This is h bar omega over kt minus 1. I can keep the first term 1 plus h bar omega over kt minus 1. These ones cancel, h bar omegas cancel, so energy as t goes to infinity becomes nh bar omega over 2 plus n times kt. Now this is the answer I want, which is, let me write it in a slightly different form. Well, the first term, for very large temperature, the first term is constant, the second term will dominate. For large temperatures, this is approximately equal to 2n times kt over 2. This is the energy. of the oscillator at very large temperatures. At large temperatures, we expect to have large quantum numbers. At large quantum numbers, we expect to recover the classical limit. This is the classical result of the energy. Well, we can do the same treatment oscillator as a classical system. In this case, Q1 would be dp dq. I'm just looking at a 1D oscillator, not 3D. So there's one momentum, one coordinate divided by 2 pi h bar. I have the exponent of minus beta. The energy of the oscillator is 1 over p squared over 2m plus 1 over 2m omega squared q squared. Both are Gaussian integrals. This will be equal to 1 over 2 pi h bar. Momentum integral will just give me square root of pi 2m kt. The coordinate integral will just be similarly square root of pi 2 pi kt divided by m omega squared. This is Q1. Okay, let's do the simplifications. Pi's will cancel, the masses will cancel, the 2's will cancel. So Q1 would be just kt over omega, the partition function of one oscillator. Qn would be kt to the power n over omega to the power n. There's also h bar. Free energy will be minus kt logarithm of Qn, which will be minus n kt logarithm of kt over h bar omega. No, so there's no, yeah, there is h bar. Yeah, I see, we are looking at the classical treatment here. H bar appears only because of this minimum volume element in phase space, which came from quantum mechanics. But besides that, this h bar over here, everything is classical. But still, somehow this h bar omega still appears. Well, it won't change the final result. For example, if you look at the energy, which is minus t squared derivative of free energy over t with respect to temperature, this will be minus t squared times minus nk over t. This is nkt. The energy is nkt. Just like the classical result. What about the pressure?
There is no V.
There's no V. Nothing depends on volume. You see, harmonic oscillator cannot exert pressure on the surface, because just oscillating over here is not hitting the walls.
It is the surface.
Hmm?
It is the surface.
Yeah, kind of the surface. It's confined in a finite volume, not because of a surface, not because of a confining volume, but rather due to the interactions. So that's why it just doesn't make sense to talk about the pressure anyway. So there's no pressure.
Was it the case in the quantum case too?
Sure.
There was no V, right? Yes.
No V, because you see, volume appears through energy eigenvalues. But if you have harmonic oscillator, the energy doesn't depend on the volume. Well, of course, you can put many oscillators in a volume, but in that case, it won't be just a harmonic oscillator. It will be harmonic oscillator plus the potential that's created by the walls. So for low enough energies, well, the energy values will be given by h bar omega over 2. But if you increase the energy, the oscillator becomes oscillating through larger and larger distances. Eventually, it will start hitting the walls, but then it's no longer a harmonic oscillator. And then energy will depend on the volume in that case, and you get the pressure. But only if your oscillators are hitting the volume. Any last questions? In that case, see you. Okay, Monday there's no lecture. Wednesday we will have a lecture. Monday is 28th of October. It's just half day. So we don't have any lectures, but Wednesday we will have a lecture.